Welcome back to Blue Pen Land here, okay? Now let's talk about energy stored in springs. And always before, when we made a formula for energy, we used the work energy theorem. That was that the energy stored in something, right, is equal to the work done on the system. But here we've got a problem, okay? Lifting a box or speeding it up, we could exert a uniform force. But here our force, this axis here is our force, right? Is nothing, and then it stretches out here and it ends up a maximum of kx, right? And so our force is always changing. The question is, what do we use for the force? Do we use 0? Do we use the maximum? And of course my vote is that we use what it is in the middle. The average force is 1/2 kx. It's half the final amount because this is just a straight line, right? So the force is 1/2 kx, right? That's because the force is, of course, kx at the very end, right? I'm using that formula, okay? And then the distance is, of course, x, and so we end up with an interesting formula, right? That the potential energy of a spring is 1/2 kx squared, okay? Where this is the spring constant, right? And that's newtons per meter, right? And then this is the stretch distance, right? And that's got to be in meters, right? So that's our formula. Now, that's an easy way to derive it, is to use this average thing. But there is another interesting way to do this, right? Is that really what we can do, there's something in calculus called an integral, and the work done, if you draw force versus distance, the work is really this area that's in there, right? That area is the work, okay? And the area of a triangle is, everybody knows, it's 1/2 base times height. So the area of this one is going to be 1/2. The base is just x, right? This is our x. And then the height is still kx, right? So it's, again, it's the area is the work is 1/2 kx squared, right? So that's another way to do this, right? And another way to do it is to just say, gee, the rectangle is, anyway, kx times x, right? So this is 1/2 of kx times x. So many ways to do it, but that's our formula. Let's apply this thing here. There it is if you want to write this down, right? I'm about to go to the next slide here. Okay, so Mary H. Little Lamb has a 24 Newton per meter spring. That's its length. See, I'm trying to make this difficult, right? And then she stretches it to 46 centimeters, right? So here it is unstretched and 31 centimeters long, or 0.31 meters, right? And then we stretch it to like 40.46 meters, right? And then the question is, what is our x? Well, our x is this much, right? So that's 0.46 minus 0.31. This is the hardest part of this, right? Is 0.15 meters is our x, right? Okay, now we're all set. Potential energy is 1/2 kx squared, so it's 1/2 24 newtons per meter times 0.15 meters squared. Okay, so I can do that. 0.5 times 24. Where's the 24 button? There it is. Times 0.15 squared is 0.27. That was somewhat underwhelming. 0.27 joules, right? Ta-da. Right, or 270 millijoules. That sounds a lot more, right? 270 thousandth of a joule. So there it is. And then, look at the units here. This will be newtons times meters squared over meters. Newton meter, well, we know a Newton meter is a joule. So all is good in physics land.